Okay, hi everyone. It's Andrew, and this video is going to act as a supplement to the practice exam that I sent out. Yeah, sent out earlier today. Right. So my thought process is that some people might find it to be sufficient to be given the solutions and they can read it on their own pace, but others might prefer having me walk them through or having a person walk them through uh, the problems themselves in the pace that we have in lecture or in class in discussion. So yeah, this is essentially going to be that. And so I'll just be completing the exam here um, in real time. So okay, so let's begin. So problem one, if you guys have the exam pulled up on your laptop, if you want to complete them and follow along, go ahead and do so. But to get started, we have problem one here. I gave you two functions j and h, and I asked you to compute the algebra of functions, right? So this is coming from 2.8, and the first one asks you to simplify the product h times j. This is going to be equal to h of x times j of x. That's going to be essentially, can you simplify and combine like terms? That's basically the exercise here. 2x plus 5 times 7x cubed minus 4x squared. So if you follow this out, you should get 14x squared minus 8x, or 14x to the fourth, 8x cubed plus 35x cubed minus 20x squared. So 14x squared minus 27x cubed, or 14x to the fourth, my bad, minus 20x squared. As so. Okay. Next, compute j minus h evaluated at minus 2. This is nothing but j of minus 2 minus h of minus 2. So j of minus 2, that is going to be 7 times minus 8 cubes minus 4 times minus 2 squared minus 2 times minus 2 plus 5. Notice that when I'm subtracting a function, I always open my parentheses so I don't forget to distribute that minus 1 or that minus sign on the inside of the sum. So this is 7 times or minus 56 minus 16, and minus 4 plus 5 is just 1, right? So minus 1, that's 73, minus 73, like so. Okay, good. And then finally, h of j evaluated at 1. So h of j at 1 is equal to h of 7 to 1 cubed minus 4 times 1 squared. Any 1 to any power is just itself, 1. So it's 7 minus 4 is 3. So 2 times 3 plus 5 is 11. So good. Moving on. Problem 2, I give you a function and I ask you to compute the difference quotient. That's what it boils down to. This is also coming from 2.8. So yeah, let's do so. G of x plus h looks something like this. So x plus h squared minus 7 times x plus h minus x squared minus 7x. So that's just minus g divided by h. Okay. And so nothing's really new here in terms of like what you have to do. All you have to do is simplify this out, right? So you have to be careful with your algebra here, your expansions. So the first term expands like this: squared minus 7x minus 7h. Remember to distribute in the minus sign for the last two terms. So x squared plus 7x. And you know that you did something right. You did it right if a lot of things start to cancel, like this x squared and this x squared, this 7x and this 7x, and I think that's it. So if I clean this up, I get 2xh plus h squared minus 7h over h. Notice how the numerators, all the terms have h in them. Factor that out. Get h times 2x plus h minus 7 over h. I get 2x minus 7 plus h as my difference quotient, like so. Now, those of you who are familiar with calculus, you can make the deduction, right? As you send h to 0, you can assert that g prime of x is indeed 2x minus 7. The derivative of g is 2x minus 7 if g is x squared minus 7x. Okay, good. All right. So, moving on. Problem 3, verifying inverses. So, this is coming from section 4.1. So if you know the definition of inverse, to verify two functions are inverses, you take the forward composition, verify that it equals x, identity. Take the backwards composition, verify that it equals identity. And then if you show that, then you can assert that they're both inverses of each other. My bad. Okay, so I have f and g. I also have this nifty thing right here, this domain restriction. That's going to be non-trivial because we have a square root, right? Remember, when we take a square root of an unknown variable, we get plus or minus, right? The positive or the negative branch of the square root. If I have this domain restriction, it's going to let me choose the negative root, right? I'm saying x to be less than 2. So keep that in mind. Anyways, moving on to do the forward transformation here, or the forward composition, f of g of x. It's going to be open parenthesis 2 minus square root x minus 4 minus 2 squared plus 4. 2's cancel, left with x minus 4 square rooted, squared plus 4. The square root and the square cancel, left with x minus 4 plus 4. And the 4's cancel, and I'm left with just x. Okay. Now, on the other hand, g of f of x is 2 minus square root x minus 2 squared plus 4 minus 4, like so. The 4's cancel on the inside of the square root, left with 2 minus the square root of x minus 2 quantity squared. Okay, so now this is the critical part, right? I have 2 minus the square root of some x term. So the square root and the square cancel, yes. But what I'm left with, if I didn't have the domain restriction, was plus or minus x minus 2. But since I'm taking x to be less than 2, less than or equal to 2, this quantity will be negative, right? Right. If I take x to be less than 2, less than or equal to 2, this quantity is either going to be 0 or it's going to be a negative number. So I have a negative times a negative, which gives me a positive, right? This negative is here, so I have a negative times a negative. Oh, I should make that clearer. So going from here, the square and the square root cancels, right? So I have 2 minus plus or minus x minus 2. But with the domain restriction, this makes me take the negative branch. So I have a minus here. So 2 minuses gives me a plus. So I get 2 plus x minus 2. 2's cancel, and I'm just left with x. So that means I can assert that g and f are inverses. And I'm done. Okay, so that gives you the work. 4, I want to ask an equation of a line. So this is 2.4 and 2.5. Those are my two sections. So 2.4 and 2.5, find the equation of a line that passes through the point 2, 3, and that is perpendicular to the graph of the line at 4x minus 2y is equal to 2. Now, when I look at this function, or when I look at this problem, I think of the given information. I have 2, 3, perpendicular, and then a line, right? Immediately, when you think, if you're given a line or a slope and a point, you should immediately think point-slope form. That's what it's useful for, right? Point slope form, you can write an equation of line just given a point and a slope. We have the point. We don't have a slope explicitly yet, but we can find it from this line right here, right? This line is in standard form. If I isolate y, I put it into slope-intercept form, and that gives me the slope. So I'll leave it to you to verify that this, if you simplify, if you get y equals on one side, this is y is equal to 2x minus 1, right? If you isolate y. So yeah. And so from this form now, you can say that m is 2, right? The coefficient of x. But we want, so this is the line. We have a line and we have a point now. And we want a line that is perpendicular to this line right here. And it also goes to the point 2, 3. So if m is 2, the line, the slope of the perpendicular line, m perp, has to be opposite sign reciprocal. Okay? So yeah, we have a slope. We have a slope. We have a point. Point slope form, right? So the equation of the line that's perpendicular to the given line is given by y minus 3 is equal to minus 1 half x minus 2, which implies that y is equal to minus 1 half x plus 1 plus 3. In other words, minus 1 half x plus 4. As such. Now, if you want to verify this even more, like on your own terms, of course you can do this on a test, but you can plot this line right here and plot this line in a separate tab in Desmos. You can see that their graphs will intersect each other where their interior angles will have 90 degree, which is indeed the definition of perpendicular. Okay, moving on. Problem 5. So problem 5. Now, this was a bit of an issue in terms of making or organizing this exam, right? Because according to the syllabus, the stuff that problem 5 and problem 6 have is coming from section 2 point or 3.1, so quadratic equations in vertex form and the vertex. Um, so it's not really on the midterm 2 syllabus, but since you guys actually covered a portion of it last Thursday in lecture, yeah, the professor and I decided that it was probably fair game to like give you this. But it's not too bad. It's not too bad. So this is actually coming from 3.1. You don't have to study that much. All you need to know is that the vertex, the vertex corresponds to the global max slash min of quadratics, and the x value of the vertex is given by minus b over 2a. I don't know if I'll go into conceptual detail before the exam, but I'll definitely do so when we cover 3.1 in discussion. Okay, but that's all you really need to know for the exam. This gives you the x value of the vertex. Okay, so going back to the problem, I gave you a context. The path of a soccer ball is after being kicked is modeled by this function, where f is the height of the soccer ball in meters and x is the horizontal distance. And the question is asking you how far, as in what is x when the ball is at its maximum height. Okay, so that's the general idea. Now, for these types of problems, whenever you see an application problem and they give you a function that is quadratic, the highest degree is 2, and you see the keyword maximum or minimum, you should immediately think about finding a vertex in some sort of way, right? That's the main idea. That's good. The question's assessing you if you can find the vertex and if you can find if it's a maximum versus a minimum. In this case, I want to know if x is the horizontal distance. I'm asking what is the horizontal distance. I'm simply just finding the x value of the vertex, right? You're basically asking you if my ball is being thrown, where am I in terms of my horizontal distance? right? And of course, f is the height. Okay? So minus b over 2a gives you the x value of the vertex. So in this case, ax squared plus bx plus c. This implies that b is 0.8, a is minus 0.004. So minus b over 2a is nothing but minus 0.8 over 2 times minus 0.004, or 0.8 over 0.008. And from here, it doesn't really matter how you compute these decimals. I usually like to write the fractions. So this is really 8 over 10 over 8 over 1,000. So 8 over 10 times 1,000 over 8, which is 100. And since my x is in meters, I have to account for the units as such. Okay. And as always, with these application problems, it's very important that you are mindful of the units and also if your answer makes sense, if your numbers make sense. Again, as a reminder, there's no such thing as a negative time or a negative distance or negative space. All right, so if you get a negative number, it probably means you did something wrong. So remember to check your work. Okay. Okay. Moving on. Problem 6. Given a function, q, can you answer some things about it? Um, so what can we say? Look at q. So I'm assuming you guys, from our previous discussion, you probably understood what the vertex form is. It's very powerful. It gives you the location of the vertex. Q is going to be a quadratic in vertex form. So the vertex here is at 3, 2. And we can immediately answer that for C, which is asking about the vertex, 3, 2. And it's also a positive quadratic, so it has an upward U shape. Okay, so the vertex here is a minimum. Minimum, which is given by the y value of the vertex. So the y value is at 2. Okay, so already you can see how powerful the vertex form is. I was able to answer an entire question just simply by looking at the function I'm given. Very useful. So that's C. So going back to A now, I want to talk about the transformations. So this is coming from 2.6. All right, so at the point that I'm releasing this video, we haven't had discussion yet, so you haven't formally worked with 2.6 material with me as yet. But let's say that you got through lecture, or let's say you're doing the practice exam after Friday, after meeting with me. Then you would know that the transformations follow order of operations, right? So the multiplicative transformations come first, and then the additive transformations. And by convention, we would like to work with horizontal transformations first, and then vertical transformations. So to go from x squared to q of x, I first need to look at q and see the transformations that I have. Okay. So in terms of horizontal transformations, it's whatever happening to the x term, the input. So what do I see? There is no number in front of the x, so that means there's no horizontal scaling, no multiplicative transformation. The sign in front of x is also positive, so there's no horizontal reflection. Okay? But there's a minus 3, so there's an additive transformation horizontally. And this is our first transformation. So I go from x squared to x minus 3 squared. And what is happening contextually? I am shifting right 3 units. Okay? So we already took care of all the horizontal transformations that are possible here. To think about vertical, what is being multiplied to the special term in this case? The square term. I think that the 2 is being attached by multiplication. I'm also adding a 2. By order of operations, we have to consider the 2 being multiplied first. Okay. So from here, I go to 2 times x minus 3 squared. And what does this 2 correspond to? Corresponds to a vertical stretch by a factor of 2, right? It's a stretch because the number in front of the square term, 2, is larger than 1. If it was less than 1, it would be instead a shrink. Okay, so bigger than 1, less than 1. Bigger than 1 stretch, less than 1 shrink. Okay. And the last thing to account for is, of course, the 2 being added. So I go to this, which is precisely the definition of Q. And this addition of 2 means you're pushing your function up 2 units. So shift up 2 units. And there we go. Transformations. Okay, good. All right. So that's A. B, ask for the domain and range of Q. So we said that Q was a quadratic, which means it's a polynomial. And by a previous discussion, all polynomials have infinite domain. So, yes. Also by a previous discussion, we said that Q was a positive quadratic, which means the vertex is a minimum. So my lowest point is a minimum, and my highest point is infinite. Right? So no need to do work for this. This is just purely conceptual understanding. All right, so we already did C, D. So if C, so the thing about the vertexes, this is also by previous discussion, since I say you've discussed the vertex already. The y value of the vertex gives you the minimum and the maximum. The x value, it gives you the line of symmetry, the location. So the line of symmetry of this quadratic is simply just x equal to 3. All right, simple enough. And so, yeah. And then for E, we want to determine the intercepts, right? The x and y intercepts. Now, already, since the range is 2 to infinity, we can already assert conceptually that there shouldn't be any x-intercepts, right? Think about the definition of the x-intercept, right? When x is equal to 0. If my range is above 0, my function can never be at 0, so can't really intersect the the x-axis, right? But let's say you didn't make that conceptual connection. You can, of course, verify this by definition by first principles. Set q equal to 0. This implies that 0 is equal to 2 plus 2 times x minus 3 squared. Or in other words, minus 2 is equal to 2 times x minus 3 squared. And if divide by 2, you can already see if you take the square, you get plus or minus an I term. And here should be where you should make that the conclusion that there are no real x-intercepts. There is a y-intercept though. Q of 0 gives me 2 times 0 minus 3 squared plus 2. So 2 times 9 plus 2, which is 20. So 0, 20 is my y-intercept. So putting it all together, for my graph, draw your coordinate plane. It goes off to infinities. And plot your points, right? Remember to label your scale properly if you don't want to make all the ticks. And label 3 points. So I have 2 points in the terms of my y-intercept and my vertex. 3, 2. To find a third point, you can just substitute any test value into Q and then get out a test number, right? It doesn't matter. Or you could also use symmetry, right? Notice that we said that the axis of a symmetry is given by the vertex, right? The location of the vertex. So 3 units to the left Um, wait. Yeah, 3 units to the left. My function's at 20. That means 3 units to the right of 3. My function should also be at 20, right? We said that quadratics are symmetric about the y-axis. So with that in mind, by symmetry, I assert that the point that is 3 units to the right of my vertex will have value 20. So 3 plus 3 is 6, so 620 is a point. So, right, good. That's the graph, right? Label 3 points, label your axes, which is good enough. It doesn't have to be perfect. And lastly, question 7. I give you a graph and I ask, can you quantify or give the characteristics? Okay. So, given this graph, z, can I find z of 4? Right? When z of 4, that's like when x is 4, where am I at? X is 4, I am here. So 5. On the other hand, if I think about it in reverse, I want to find when z is 3. So when the function is equal to 3, as in when y is 3, where is the x? I'm here and I'm here. So if I go down to the x values, that's going to be minus 4 and 2. Okay. C, the domain, shouldn't be hard to convince yourselves that the domain is all reals. It's continuous. The range, well, everything is continuous again, like we said. But also we can see that there's a lowest point, right? That's given by this point here. And the y value is at minus 1, and I'm going all the way up to infinity, so minus 1 included infinity. That's my range. For E, intercepts, where does the function intersect the x and y intercept? Here, here, and here. So minus 3, 0, minus 1, 0, and 0, 1. That's so. F, intervals where z is constant, should convince yourself that z is constant nowhere. So you can write the empty set, 2 brackets, or not applicable. Z, so for G, or Z is increasing, as you read the graph from left to right, where are you increasing at? Well, visually it looks like you're increasing here and also here. Now this point is interesting because it's a sharp point, right? This is the point where the two different functions meet. And by the notion that we had before, we don't actually know if a if a point can be increasing, decreasing, or constant at a single point. So in that case, we omit the point, right? The sharp point is omitted. And if you guys are familiar with calculus, this sharp point is also not differentiable. So we would just take this line right here, this line right here, and then this interval right here as two disjoint open intervals. The minus 2 to 3, union 3 to infinity, like so. Okay. And then for decreasing, you can see that you're decreasing on this interval. So minus infinity to minus 2. And again, be very clear that any answer for increasing, decreasing constant, you must simply have open intervals. Because again, we don't know what it means for a point to be a single point, a singleton, to be increasing, decreasing, or constant. So no brackets at all. No brackets. Okay. All right. For I, is there a relative minimum? Yes. It's right there. Yes. And then the minimum is the y value, so y is equal to -1. As so. Is this graph a function? Yes. Vertical line test, guys. You can see that it satisfies us anywhere. However, it's not one-to-one because of the horizontal line test. Yes, no. And that is the practice exam. Okay. So hopefully this was useful. Um, this won't be the last time that I'll make this video, because I have to go to a wedding in like about a month. And so that week I'll have to cancel discussion, and then instead I would, record an hour-long lecture, and that would be the replacement. But in terms of this exam, please use this as a resource. Don't use it solely as your only resource. Do look over your notes. Do look over the other resources they gave you and the resources in the modules tab to have a well-rounded study plan. Okay. But other than that, I wish you guys luck on midterm 2, and yeah.